Okay, so I said we can't really change our soil texture, at least not very easily. If we're doing something where we have, control of a small area, maybe raised beds or even greenhouse types of things, which in which case you're probably using a potting soil type mix, and some of what we're talking about doesn't necessarily apply to that. But in raised beds, yeah, you could bring in some soil and mix it the way you wanted to, or import some that had the characteristics you like. But most of us, who, if we're not doing that, if we're farming on anything larger than a few raised beds, we're kind of stuck, or maybe happy to have the kind of soil we do, the soil texture. But a lot of times, people, probably the number one question I would get at some social gathering, oh, you're a soil scientist. How do I fix my texture? It's all clay. Um, you you can't change it from being, and it's probably not really clay. It's probably a clay loam or even a loam, but it feels hard to work to them. Probably it's a little bit lower in organic matter than it could be. And adding organic materials together helps bring helps. Well, I'll talk about how that works in a minute. But adding organic materials does increase the amount of aggregation you have in soils. If you can minimize how aggressively you till, how much breaking up of those aggregates you do, that will also help make the soil more workable and probably get toward what you want to do in terms of fixing your soil. Avoiding compaction is another one. So most of those examples I just talked about were, people who feel like their soil has too much clay and it's too hard to work. Kind of at the other end of the spectrum are soils that are very sandy, and you kind of wish you had some clay in there because the water just moves right through those soils, too fast really, and it doesn't have good nutrient holding capacity. And in that case, you might wish you had less sandy of a soil. And again, the answer is add organic materials there. It'll help aggregate those sand particles and have it act like it has finer pores in it as well. And like I said, we'll talk about aggregates and their importance in a little bit. Let's see. Okay, we're just checking on where we are. So I know you've done a little bit of work. Cinda told me that you talked about soil surveys a little bit. So one of your resources. And that's really one of the best ways to find out what soil texture you have. You can take samples and get them sent to a lab and have a soil test run on them to get your percent sand, silt, and clay, your particle size distribution. But you can also go now online, formerly books, and some of you may know what I'm talking about with respect to the books with the white cover, which are pretty much all out of date. They've all pretty much been revised since then. So you want to go online to the Web Soil Survey, and the link is right here. There's also a mobile app for knowing your soil type. I'm not sure my grammar is perfect there. Mobile soil type app. It's a soil type mobile app. Maybe that would be better. UC Davis put together. And you can take your smartphone and be there in the field, and through the GPS on the phone, it will say, oh, you're in this place. Here's what your soil type is. Okay. And hopefully you've already looked at soil types and soil surveys, and sort of vaguely know what they are. Essentially, you'll see some maps. A soil mapper will be out in the field and kind of look at the soil and decide it's this type or that type, and then they'll kind of draw the boundaries of the extent of that particular soil. If you look at the map here, you can kind of see, looks like it might be a highway or a drainage ditch or something like that, and maybe some little buildings. Just to give you an idea of a scale, this might be a little home site. Let's see. The really useful part is once you know which of those soil types you're interested in, you can look up all sorts of information about them. There's lots of tables of information that can tell you the physical properties, chemical properties, potential for growing mostly agronomic crops, but it depends a little bit on where you are. They're adapted to the counties that they're in. So anyway, so that's kind of what's in the soil survey. Here's a picture of what the screen looks like when you go into it, and I won't spend a lot of time on, we're not going to actually explore it, but I do have my main point is to look at the getting started with web soil survey down in the bottom right hand corner of that home screen, because it's not that intuitive to the average person. And I'm a soil scientist, and to be honest, it was not intuitive to me to figure this out. It's put together by people who use GIS systems, geographic information systems. So they think in terms of different layers of data and maps and everything. So you really want to look at this getting started with web soil survey so you don't get totally lost. Once you read that, it's going to tell you, that the very first place to start is that green button that says start the web soil survey, and then this points out some of the highlights of what you can do there, but essentially you have to go find an area of interest. And once you're there, you can use those tabs will tell you all sorts of different information, or the maps, different things like that about the soil. So that's something that's kind of fun to explore. It does need a decent internet connection, I found. You definitely couldn't do it under dial-up at all, and even a satellite internet that I have, it's pretty slow. But at work on broadband, it's not so bad. Okay, so that's how you would know about your texture and lots of other characteristics. There's a couple more points I wanted to make about the components of soil. And what we're going to look at here is actually the clay particles that are less than 0.002 millimeters in diameter. And in fact, if they're less than 0.001 millimeters, they're called colloids. Whether they're mineral, most of our organic matter would fit into that category as well. And a lot of people just lump all of the clay into that category as well. What's really important about this, and why we even bring up this word colloid, is because at the molecular level, these materials are very reactive, okay? But because they're so small, they have a tremendous amount of surface area per unit volume. Okay, they're, instead of having a cylinder that was, I don't know, like a water bottle size, if you broke that up and had a million little water bottles packed into that one water bottle, think of all the surface of those little water bottles along those lines. And in fact, I have kind of a fun calculation on this page here. If you were to have sort of a fine textured soil, so maybe like a clay loam, silt loam maybe, and you took a hectare, which is about the size of a U.S. football field, and went down 5 feet, 1.5 meters. If you were to look at what is the surface area of the soil in there, and most of it's on those colloids, like I said with that water bottle example, you would have over almost 9 million square kilometers of surface area that reactions can be happening on. And how big is 8.7 million kilometers squared? That's kind of a number I can't really imagine. Well, it's about the total land area of the U.S. So a lot of surface area is embedded there on those surfaces of all those small particles. So this is really important, because the thing about these surfaces is they have charges, and some of you may remember some chemistry, or maybe you're really up on it, but there's positive charges, there's minus charges, and then there's other types of functional groups coming off of in the molecular structure that are attracted or bond with other materials, like even organic pesticides, or I don't mean organic pesticides what I mean is organic molecules such as a pesticide, or as soil organisms have organic structures on them, using kind of that carbon-containing, I guess, definition of organic. I hope I didn't confuse anyone there. Put it in the questions if I did. Hopefully that's clear. But anyway, lots of things will bond, especially to the organic matter, but also the clay particles. And that's where lots and lots of reactions happen. So that's part of our turnstile and endless procession of atoms, because they get absorbed onto those surfaces, and then they get replaced by something else and taken up by something else. So there's all this movement, really. Okay. So kind of tying up that section, I guess, on the components of soil. We had organic matter, minerals, air and water, and we'll talk a little bit more about the pore space. But Organic matter is really key as a management tool. Okay, and that's what I want to emphasize here. This particular book, and actually there's a newer edition up there now, Building Soils for Better Crops, and it probably has come up earlier in the class. It's available online through the SARE website, and you can download it free or order it for, I think it's $19 or $24, something like that. It's not very expensive. It's a great resource. Okay, so another basic property we want to talk about is how these particles come together into forming aggregates. And the pictures I show here, we use the word structure. And soil structure is, just all by itself, nature forms these aggregates from those chemical reactions and physical pressing and freeze-thaw cycles and things like that. On the right side, you're seeing some granular structure, and that's probably what a lot of us would like to see in our seed beds if we're planting. If we look down in the subsoil, you can have these blocky and prismatic type soil structures. These are all totally natural. These aren't human induced or anything. Okay. What's important about these is that there's spaces between these aggregates, between those little grains on the previous slide, between the walls of these different blocks or prisms. And that's where water, air, and roots can get into the soil and dig more deeply. If we look down at the particle level, you'll see that organic matter and humus, in this case, and clay come together, they bond together, they bond the individual particles together, and you end up getting this little tiny sort of micro aggregate here. And as you scale up, you get macro aggregates and larger micro aggregates, and it's a nested structure, I guess, going up through there. And as you get larger, you're increasing avenues for aeration, infiltration, habitat for organisms, rooting for plants. The micropores, which are can be between the aggregates in the very small cases or within the aggregates, that's where our water gets held. Our fine roots can go in there. Some of our organisms are in those sites. So that's how come we can have water move through it, because it moves through the macropores, but water gets stored in the micropores. So, and I like to think of it, the macropores, as being like one of those big fat sponges you use to wash your car, which is great, but if you spilled milk in your kitchen, it wouldn't be the best at soaking it up. You'd really want to grab for that paper towel or something like that, or some microfiber cloth, because it would suck that right up. That's kind of the difference, macropores in the big car sponge and the micropores in the what you're cleaning up your spilled milk with. Okay. Another, I guess, a comment on aggregates is they can get broken. They're fragile. The more organic matter you have, the more stable they usually are. But when you get your aggregates broken up, you lose those larger and medium-sized pores that are important for air and water infiltration. You also lose your total water, or your total porosity, excuse me. And then finally, I drew this little graph here, just a generic graph, but it kind of shows that if you do have to till, which usually we're trying to prepare a seed bed or something, if you do it in a wet soil, the water content goes up. The density, the compaction of the soil goes up too. So we really want to avoid doing any tillage in wet soils. A quick comment on soil water. I think we already talked about this with the sponges, but think about capillary tubes. Like if you ever had a blood draw out of your finger, that'd be like a little tiny pore, right? The blood kind of gets sucked up right into that tube. That's the same forces, those capillary forces, that pull the water into your microfiber cloth you're cleaning your floor with, or your very fine soil, very small soil pores. And I think probably most of us have done something like this with straws, and we notice a little bit of water can get held in the straw, or maybe it's our pop or whatever. And that the wider the straw is, the less water it can pull in. And when you have good aggregation, you have both large pores and smaller pores. Okay.